Hello pre-calculus students, and welcome to a short video on piecewise defined functions. This is the third video on piecewise defined functions, and the ones that we had before were focused on linear functions only. And as you can see, the objective here is to get anything in the Cartesian catalog. The Cartesian catalog is nothing other than what you have in the Chapter 2 review, which is just a catalog of the parent functions that you all are familiar with by now, including constant, identity, square, cube, square root, cube root, reciprocal, absolute value that are down here, and then greatest integer function is in there, although we're going to talk about that next week. Okay, so we're not going to do any of those today. We're going to focus on piecewise functions that are not, the other 8. All right, so let's take a look at what we have here for our first example. So we have a piecewise defined function. Remember that means it's a function that has a different rule for different parts of the domain. And for this first example, there's 3 pieces. For here's after the comma, that's the part of the domain. So the domain is on the right, and the first 2 are linear functions, and the last one is a quadratic function. So we're only going to look at the part of the quadratic function that is to the greater than 1, or to the right of 1, with an open circle at 1. Okay, so let's see what we have when we graph these pieces. Let's just first answer a couple of basic questions about the function to make sure we understand what this notation even means. Okay, so first of all, what would f of 0 be? So in order to find f of 0, you need to know which rule to follow. So you need to find out which domain includes 0. And so this is greater than 1, doesn't include 0. This is just 1, that's not 0. And this is between -1 and 1, so this is the rule that we follow for f of 0. Okay, so f of 0 follows the first rule, which would be the opposite of 0, which is just 0 plus 1, or 1. So f of 0 is 1. Okay, f of 1, again, we have to figure out where that applies, and that's right here. That's the middle branch of this, and the output, when the input is 1, the output is 2. And f of 2, 2 is in the third branch because it's greater than 1, and so we're going to square it. So we're going to get 2 squared, or 4. Okay, so that's pretty much how you read these functions. Now let's determine the domain of the function. Well, the domain is given to you. You just have to piece it together. So all of this stuff over here is the domain. All we have to do is piece it together and see what we have. Now it's everything in any of these, so it's like an OR statement. So if you want, you can put this on a number line. You can include all the points here, which is -1 and 1, and let's see what we get. So we have -1 to 1. Now here we're including -1. Actually, we're including everything between -1 and 1, but just not including 1, right? So this is from -1. Now, is there anything here less than -1? I don't see it. I see the lowest point here being 1. So I'm going to put a circle there. Everything up to an open circle here. So that would be part of the domain from the first branch, from the first piece of the piecewise function. The second piece fills in that hole, right? Because now this function is, in fact, defined at 1. So we're going to fill in the hole. We definitely want to include that in our domain. And then the third piece, goes everything greater than 1. So it's just going to continue on like that. We're doing the opposite of breaking it down into different intervals. We're trying to see what there is here altogether. And it's pretty much everything greater than or equal to 1, including 1, even though there's a hole here, including -1, including 1 because it's filled in here, and then everything greater than 1. So the domain, so B, here, let's just do this, B would be from -1 to infinity, including -1. Okay? We're going to graph the function. Okay, so let's take a look at the graph. So when we graph piecewise, I like to have a couple of tools. I like to have a pencil so that I can erase, just sometimes make things a little bit less confusing. And I like to have a highlighter so I can really emphasize what is part of the final graph. All right, so let's see what we have here. Now I'm going to use, let's think about the scale for a minute here. our numbers are pretty small, and the scale here, the graph is pretty small. So I think it's going to make things a little bit easier if we make the scale like this. So we're going to make it, instead of making each tick mark 1, I'm going to make this one over here. It's still going to be small, but it will be a little bit easier to manage that way. So this is 1 right here. Okay, we don't have to put all the numbers. And we'll do the same thing in the y's. So 1. Yeah, I think it's, it's kind of arbitrary whether you make these stretch out the y's or not, but we'll just do it. And we might go off the graph a little bit with one of our points. We'll see what happens. All right, so now I'm going to get the pencil, and I'm going to just graph the first piece. So I'm going to graph this line, y equals negative x plus 1, as I would normally graph it, as a y-intercept of 1 and a slope of negative 1. So a y-intercept of 1 and a slope goes downward, negative 1, so it's something like that. So the graph will look like this. Again, just graph it like normal. Then we'll think about the domain. That's just the way I like to do it. All right, so this is between negative 1 and 1. So I only want it from here. Let's zoom in on this so we can really see what's going on. Okay, I only want it from here to here. So I want to include the endpoint based on what I see right here. I want to include the endpoint on the left and include a hole on the right. All right, so let's do that. So the endpoint on the left will be at negative 1, so there's going to be an endpoint there, and a hole on the right, which is right there. Now let's just make sure that we have those exact points. Right, so this goes from x equals negative 1 to x equals positive 1 with a hole at 1. But let's just see what those values are. Did we already find them? We found the value at 1. We found f of 1 already. And f of 1, we know that that's 2. Well, there's a hole there. So, well, we may as well plot that point. We know it's there since I just mentioned it. There is going to be a point there. This hole is not going to get filled in. So this hole here would be, I guess we can't really zoom in. This hole here would be at, there's going to be a hole at negative 1, the opposite of negative 1, right? So negative, or the opposite of negative 1, plus 1, which is 2. So there's going to be a hole where the input is negative 1 and the output is 2. And, sorry, that's not a hole, that's the end point. So let me cross that out, that's the end point. That's that one right there. Okay, there's going to be a hole where we have the 1 right here. So when we input 1, that's where the hole is. So I'm going to put the opposite of 1 plus 1. So the opposite of 1 plus 1 is 0. So there's going to be a hole at 1, 0. And that's just what it looks like on the graph. So we're good with that point. It ended up right where it's supposed to be. All right, and that's it for the first branch. So let's just highlight what we have here. We have a point here. We have this part of the graph. And we have a definite hole there at the end. All right, that's the end of branch 1. Branch 2 is horizontal. Actually, it's not even horizontal. It's just at a single point in the domain. So there's not even going to be an interval there. There's just going to be the point 1, 2. And I've already got that graph. So let's just highlight it. That's the end of the second branch. All right, now we're ready for the third branch. The third branch is a parabola. So let's just graph the standard parabola. We know how to do that. And it goes through 1, 1. That's here, actually. So it goes through that point. It also goes through 2, 4. So over 2, up 1, 2, 3, 4 would be right about there. So it goes through that point. So it's going to be something like that. I missed it. Oops. All right. And then it's going to do the same thing with symmetry on the right side. Remember, we adjusted our scale. So this is negative 1, negative 2, and then 1, 2, 3. Right about there. So it's going to go up like that. That part doesn't even matter because all that matters is the stuff that's greater than 1. So again, I'm going to cover up what I have here. There's my paper. What I have here to the left, I'm going to cover that up because all I care about is the stuff in this parabola that is to the right or greater than 1. So I know that there's a hole at 1 squared, which is 1. So there's a hole at 1, 1. That's my last one. Hole at 1, 1. That's the last endpoint or end hole on this. Whoops. So let's see what we got. Okay, we have, it looks like the graph at 1, 1 is right there, so we're going to make that a hole. This is, again, why we use a pencil, so we can erase. And this is the part of the graph that we care about, so let me highlight it. It goes on forever. It starts, oops, I didn't mean to fill in the hole. It starts at that hole. Let's make sure that that's clearly a hole at 1, 1. Okay, there's the graph. So it's got a little piece of a line for the first branch. It's got a point for the second piece of the function, and then it's got part of a parabola for the third piece. Okay. Oh, we didn't do one thing here. We didn't look at the range of this. So if we look at this function, we look at the range, we've got all the y values above 0. So even though there's a hole here, it doesn't matter because that point is still accounted for. It's still part of the range. There might not be a y value of 1 at this piece, but there's a y value of 1 here, so it's in the range. So everything greater than 0 is in the range. So the range goes from 0 to infinity, not including 0 and not including infinity, and that's the range. Okay, let's look at the next example. So why don't you look at these, take a minute, and see if you can figure out parts A and B. Okay, so first thing, f of 0, pretty straightforward. F of 1, however, not so straightforward, because you look at this one, it doesn't include 1. You look at this one, it doesn't include 1. You realize, I don't know what to do for 1. In fact, it's not defined. You're not told, it's not part of the function. It's not in the domain. F of 1 is not defined. F of 2 requires this one. Now, if you want to round this to a decimal, because maybe you'll need it for the graph, on your calculator, I want you to try to remember that the cube root is 2 to the 1/3 power. So you need that on your calculator to really find these roots. So you go 2, raise it to the parenthesis 1/3. And that's an Algebra 2 skill that I hope you guys remember. That means the cube root, and it's approximately 1.25. We'll call it 1.26. So approximately 1.26. We can call it 1.3 because we can't graph that specifically anyway. All right, and then part B, the domain, notice that we have everything starting at 3, including the -3, including the endpoint, but there's a hole at 1, and then it goes on forever. So the domain would be -3 to 1, union with, but not including 1, right? Exclusive of 1. Union with 1 to infinity. There's the domain. Okay, let's see if we can come up with a graph of this. So I'm going to graph both of these functions in pencil, not worry about their overlap, and then we'll talk about endpoints. Okay, so let's just graph those two functions. And by the way, I'm using the scale, every 2 squares would be 1 unit. All right, so what I've done is I've graphed the absolute value function and the cube root function using the scale that I gave you. I notice over here that I've got a point where the input is -3, so the absolute value of -3 is 3, so I've got a point at -3, 3, and this indicates there's a hole at the end hole. Really, it's like the end of this piece of the function at 1, 1. When you plug in 1 here, you get 1, 1. Okay, and then for this one, there's a hole because of that greater than. There's a hole when we input 1, we output 1. So both of these pieces are going to have a hole at 1. So right here at 1, instead of a point there, I'm just going to erase the point and make that a hole right there at 1, 1. Okay, both functions go through that hole, except one's going to start there. This is the one that's greater than 0. It's greater than 1, I mean it's going to start there. So the cube root function starts right past the hole and goes like that. And the other one ends there. So the absolute value function, which is the one that's straighter here, goes straight there and then straight up here, and it continues up to our point at -3, 3, right there. And that would be our entire function. And the range of this function starts at 0, goes up, there's a hole here, but it's covered here, so 1 is still in the range, and it continues all the way up past here because this goes up forever. So it's 0 to infinity, and there it is. I hope you found this helpful.